Welcome to today's Explainer. We're jumping right into a totally fascinating astronomical target known as Caldwell 54 or NGC 2506. But we aren't just talking about a simple cluster of stars today. We're actually opening up an ancient cosmic time capsule. This thing is a brilliant celestial laboratory holding the deep secrets of stellar evolution, and by the end of this explainer, you're going to see exactly how astronomers use it to read the literal history of our galaxy. So, let's dive right in. To really wrap our heads around what we're looking at, we have to start with the sheer scale of our subject. 12,700. That's the distance in light years between Earth and Caldwell 54. It sits deep out there in the Milky Way, right at the border of the Monoceros and Puppis constellations. Just think about that for a second. The light we're analyzing from this cluster today, it actually began its journey toward our telescopes thousands of years before the dawn of recorded human history. And when we finally capture that ancient light from a cluster first discovered way back in 1791 by the astronomer William Herschel, by the way, we see a massive, beautiful grouping of stars held together by gravity. But to astronomers, this is way more than just a pretty picture. It's a meticulously structured data set waiting to be decoded. Which brings us to a really crucial concept. Astronomers refer to Caldwell 54 as a galactic stellar laboratory. Now, you might be wondering, why call it a laboratory? Well, testing theories of stellar evolution is usually incredibly difficult because stars out there have wildly different ages, distances, and chemical makeups. It's like comparing apples to oranges. But in an open cluster like Caldwell 54, all of these stars formed from the exact same molecular cloud at the exact same time. They give us perfectly controlled variables. It's essentially a natural laboratory for our cosmic experiments. But of course, doing experiments in space comes with hurdles. The cluster's projected against this massive backdrop of random Milky Way stars. They're basically photobombing our data. Separating the true gravitationally bound cluster members from these random background field stars is notoriously tricky. To solve this, researchers rely on ultra-high precision data from the space-based Gaia mission. They meticulously track the proper motion and parallax, which is essentially how these stars shift and move from our perspective of every single point of light just to see which ones are actually moving together. And getting that right takes some serious dedication. Get this, 41 years. That is how long a team of scientists spent gathering data for a single comprehensive survey of this cluster. Over 4 decades, they collected an astonishing 12,157 precise radial velocity measurements. They were tracking the exact speed at which these stars move toward or away from us, all just to isolate the true member stars from the background noise. It's an absolute testament to the sheer patience required to decode the universe. Well, all that patience absolutely paid off. You can see the scientific method in action here. Back in the early 1980s, older studies estimated the age of Caldwell 54 to be about 3.4 billion years old. But as our technology leveled up, thanks to those decades of precise measurements and that fresh Gaia data, we've been able to correct the record. Today's modern studies have firmly locked in the cluster's age at approximately 2 billion years. To pinpoint that 2 billion year limit, astronomers use an ingenious tool called a color magnitude diagram. Basically, it plots the brightness of the stars against their temperature or color. Astronomers map the actual observed stars onto theoretical curves called isochrones, which model how stars age over time. By matching the real stars to these curves, scientists can literally read this 2 billion year old cosmic clock right on paper. And as a bonus, this process proved that the cluster has a surprisingly metal-poor chemical makeup. But here's where it gets really fun. As we map out these normal stars fitting perfectly onto our theoretical curves, we inevitably stumble upon the rule breakers. Caldwell 54 isn't just home to well-behaved, predictable stars. Not at all. It is packed with strange, stellar oddballs that completely defy our standard expectations of physics. The most famous of these rebels are known as blue stragglers. These are stars in a cluster that appear significantly younger, bluer, and more luminous than they have any right to be. Remember, we just established this entire cluster is 2 billion years old. All the massive, hot blue stars should have burned out and died a long time ago. Yet here are these blue stragglers, still shining bright blue, looking like they simply shouldn't exist in a cluster this old. And they definitely aren't the only mysterious residents hanging out in there. Researchers have identified 14 of these impossible-looking blue stragglers in Caldwell 54. Alongside them, they found 15 Gamma Doradus stars. These are wild, sci-fi-sounding stars that experience strange internal oscillations, causing their light to fluctuate over periods of hours to days. Throw in a handful of rare yellow giants and ancient white dwarfs, and we're looking at a truly chaotic stellar zoo. So, how in the world do we explain stars that look millions of years younger than their actual age? Well, the key to unlocking the mysteries of the blue stragglers and confirming the exact age of the whole cluster lies in a specific type of star, the ones that don't fly solo. The answer, it turns out, is all about the binary star puzzle. Recent surveys reveal that a massive 35% of the stars in Caldwell 54 are actually binary systems. That's two stars locked in a gravitational dance orbiting each other. But here is the massive twist. When researchers specifically looked at those impossible blue straggler stars, they found that at least 64% of them are locked in these binary pairs. This suggests these oddball stars are getting their youthful blue appearance by literally siphoning off mass from a companion star or maybe even merging with them completely. To actually prove this, astronomers hunt for a very specific phenomenon called detached eclipsing binaries. By filtering the cluster's chaotic movements through radial-velocity data, they look for pairs that orbit perfectly edge-on from our perspective, meaning they actually eclipse each other. Watching these eclipses happen acts like a giant cosmic microscope. It allows scientists to directly measure the exact masses and physical radii of the two stars with incredible precision. And remember, doing that is normally impossible for stars sitting 12,700 light-years away. So how do we use that microscopic precision? It's a beautiful three-step scientific procedure. Step 1, astronomers measure the precise masses of those eclipsing binary stars. Step 2, because they know the exact mass, they can firmly anchor those theoretical isochrone curves we talked about earlier. Boom, no more guesswork. And step 3, with the curves anchored by hard data, they completely lock in the exact age of the cluster at 2 billion years. Okay, so we've used our cosmic microscope. Now let's zoom back out to the macro level for a second. Scientists can also track the proper motion kinematics of the cluster, essentially tracing its movement through space. By analyzing this data, they can map how the entire Caldwell 54 cluster orbits the center of the Milky Way. And what they found is that it travels in a surprisingly regular, circular path right through the galactic disk. Now, why does that macro movement actually matter to us? It all comes down to a field called galactic archaeology. By pinning down the exact 2 billion year age of Caldwell 54, confirming its metal-poor chemical makeup, and mapping out its circular orbit, astronomers aren't just studying one isolated cluster. They're using this cluster as a vital puzzle piece to reconstruct how our entire Milky Way galaxy formed, evolved, and distributed its heavy elements over billions of years. Which leaves us with a really fascinating thought to wrap up our explainer today. Caldwell 54 is just one single cluster. Yet it took 4 decades of observation, space-based telescopes, and meticulously measuring eclipsing binary stars to finally unlock its age, its blue stragglers, and its role in our galaxy's history. If this one-time capsule holds this many secrets, what else is hiding right now in the vast, metal-poor corners of our deep universe, just waiting to be deciphered? Keep looking up, keep asking questions, and I'll catch you in the next explainer.